black holes. So to start, the purpose of this lab is to show the relationship between momentum and force and to explain how gravitation and the net force are critical to determining a system's velocity or mass. We find the mass of a black hole using an online computational model glow script, and we do the same for determining the initial velocity of a spaceship using the black hole's mass. So what we find through this intro is that the model and fundamental principles used are Newton's second law, which shows that an object's change of momentum is proportional to its acceleration and inversely proportional to its mass. And in this case, we look at F net is equal to F parallel plus F perpendicular. We also look at the gravitational force, which explains that there is an attractive force between any objects with any mass. Also, for a brief preview of this lab, we see that the mass of the black hole is 8.6 e to the 33 by determining the star's mass and the gravitational force formula. And from there, we will find that the spaceship's initial velocity needs to be negative 3.1 e7 meters per second in the x direction and 2.9 e6 meters per second in the y direction to not get sucked into the black hole. So, to expand on these main physics principles and formulas, we see the gravitational force formula on the left and the F net formula, Newton's second law, on the right. And the reasoning for using these two formulas is to show the pull between the black hole and the planet, and also Newton's second law will show the net force, which helps us to understand the parallel and perpendicular components. So, any assumption about this lab 3 is that the black hole will suck the spaceship in if we get too close, and that the black hole's mass is large enough to have this gravitational force. So what we find is that the surroundings are the black hole and all of space, and the system is a spaceship. Some initial conditions for the star in part 1 is that the star's mass is 2.0 e30 kilograms, and gravity is this constant. Also, the black hole is positioned at the origin. So details about the experiment. I first calculated the mass of the black hole using the perpendicular and parallel forces, and I used F net in the gravitational formula to find the mass of the black hole. Using the black hole's mass, I produced part 2 of the lab, finding a way to get around the black hole and not crash into the planet. I did this by using the gravitational formula on all components and systems, using trial and error on the initial velocity in x and y directions to find VIX and VIY. So first, finding the mass of the black hole, we see that we need to use F net first, and once we get that, using the perpendicular and parallel components, we can plug that into the F net part of the force of gravity, the gravitational formula, and from there we can find MBH, which is 8.65393 e to the 33. Then, for part 2 of the lab, we need to find the initial velocity of the spaceship to get around this black hole while not crashing into a planet. And what we find is that we need to first get the F net parts and then plug that into, and then also find the F gravitational force for each. And we need to find the initial conditions by using trial and error. So what I found overall was that the spaceship's speed in x direction was negative 3.1 e to the 7 and 2.9 e to the 6 after lots of trial and error. So some possible sources of error. As I said, this was trial and error, so it was a guess and check method, which is less precise rather than a computational system that would be different. And also for the what does it mean question, it asks how the net force its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. What we find is that the net force, you need to find each force acting on the system, and you add these forces together to get net force. But while the rate of change of momentum is, you just need to know the change in momentum over time. And it's easier to calculate because you don't need to know every different force acting on the system. For our what if question, I was asked what initial velocity the spaceship would need in order to be in an orbit around the black hole. And again, I tested through trial and error and found that roughly negative 0.2 e to the 7 meters per second in the x direction and 7.6 e6 meters per second in the y direction is a very close approximation to what we would need.